Virtual machines are a concept used to run multiple operating systems on a single physical host. Hypervisors are widely used, ranging from simple on-premise Proxmox setups to large cloud infrastructures with services like Nova from OpenStack. But how does virtualization actually work under the hood? Let's find out. First, we need to understand some important concepts. CPU. On a physical computer, you execute instructions on the central processing unit, the CPU. Usually, we send instructions to the CPU via control unit. The control unit then decodes and orchestrates them and sends them to the arithmetic logic unit, which itself performs the operation. To store temporary values, the CPU has a set of registers where it stores small amounts of data, like the operands used in our next operation. Modern CPUs also have multiple privilege modes like user mode, kernel mode, or hypervisor mode, which determine the access to certain resources in the CPU. Executables. From a higher level perspective, we use executables to perform some kind of operations. So how do executables work? Let's take a quick dive. When you run an executable, it typically contains multiple sections like the data section, the read-only data section, and the text section. The actual instructions are found in the text section of the executable. Those instructions are already linked, which means that the program definitions, like for example this C++ function definition, are mapped to virtual memory addresses. Virtual memory addresses are not akin to physical addresses in the RAM. This makes them portable between different RAM modules. To now execute those instructions, we need to load them into memory. Modern operating systems do not load the full instruction set at once. Instead, they split the instructions into so-called pages and load the page table to memory. In a nutshell, this page table tells the CPU which page maps to which physical frame in the RAM. Such pages usually have a size of 4 kilobytes. The virtual addresses we talked about are constructed using the page identifier and the offset value, which is the index of the instruction inside the page. The CPU will now use its prefetcher to fetch the initial pages from the memory. In order to do so, the operating system's loader will now push the initial page to the physical memory block. From now on, the CPU will use the memory management unit to translate virtual addresses into physical addresses. For this, the memory management unit does a lookup to the mentioned page table. If the page required is not loaded, a page fault is sent to the operating system's page fault handler, which then loads the required page to memory. To reduce latency for the page table lookup, there are mechanisms like translation look-aside buffer, which caches recent lookups directly in the CPU. Process context switches. When you run a process on your computer, like Civ6, it won't have access to any other application's memory space. Still, it can consume all memory available on the computer. But how does this work? As already mentioned, a single ALU can only perform one operation at a time. To make it look like multiple processes can run in parallel, the operating system performs so-called context switches, where every process gets a proportion of the CPU time. In order to switch the context, most general purpose registers, the program counter, the stack counter, and some other registers must be saved to memory. Then the state from the new process must be restored from memory so it can perform its instructions. Note that this context switch will not change the privileged registers used to run the kernel. You may have noticed that the new process could potentially use the same virtual addresses as the old process. So why does the new process virtual address not point to the physical address of the old process? Well, this is solved by pointing the memory management unit to a specific page table. As every process uses its own page table, the memory management unit will now point to the new processes page table, which itself points the virtual addresses to a different physical memory location. The context switch also involves some other operations. Like in many CPU architectures, the translation look-aside buffer is wiped on every context switch to prevent unauthorized memory access of a process. Virtual machine context switches. Like processes, virtual machines are also isolated from each other. Similar to processes, virtual machines therefore also perform context switches to create the illusion of machines running in parallel. For Type 2 hypervisors, the context switch is usually a process context switch, because the virtual machines run on top of the operating system. On Type 1 hypervisors, typically found in production hypervisor systems, a full virtual machine context switch is performed. Unlike a process context switch, the virtual machine context switch must save the whole CPU state, including all registers and configuration like the memory mapping in the memory management unit. Those operations are typically supported by hardware enhancements like AMD-V or Intel VTX. Now, if we're talking about paravirtualized virtual machines, the machines will need to communicate with the hypervisor host. In order to do so without performing a full virtual machine context switch, the CPU state is saved to memory in a structure often referred to as a virtual machine control block or structure. After that, the CPU is put into hypervisor privilege mode, which permits access to things like I/O operations. Then in the next step, the CPU fetches pages from a memory block specifically allocated from the hypervisor and executes the instruction set based on the action which invoked the switch. Such a switch to the hypervisor can be invoked primarily in two ways. The first one is a trap. Trap is called if a virtual machine tries to perform actions it's not allowed to. An example for this are I/O operations. If no drivers are installed, communication with I/O devices happens through those traps. If the VM tries to perform an I/O operation, a switch is performed and the hypervisor will handle the operation. The other option is the hypercall. With a hypercall, the VM can communicate directly with the hypervisor. For example, if virt I/O drivers are installed, those drivers can do a hypercall which then performs the switch and calls the requested operation on the hypervisor. Finally, hypervisor mode is disabled and the state of the virtual machine is restored. That was virtual machines under the hood in 100 seconds. I hope you enjoyed. If you have any other questions, let me know in the comments.